Yes, welcome friends. Let us go for the next part of discussion of alkali metals that are some important compounds of sodium. Even sodium is also important, but we will start our discussion with the sodium chloride. Sodium chloride. Sodium chloride is having formula that is NaCl, which is ionic compound, which is generally found in seawater. The natural source of the sodium chloride is the seawater. At an average, almost all some 3% of seawater is consisting with the sodium chloride, and it occurs in the form of rock salt as well as the halide deposits also, having general impurities like calcium sulfate, sodium sulfate, calcium chloride as well as the magnesium chloride. Whereas this calcium chloride as well as magnesium chloride are deliquescent in nature because they are having high polarizable power containing cations. They take up water and they are present in the form of their hydrated salts. Due to this reason, in rainy seasons, the sodium chloride becomes very wet in nature, whereas the preparation of sodium chloride is possible by evaporating the seawater to the maximum extent. The saturated solution of sodium chloride is prepared, and in the industry, after preparation of saturated solution, through that saturated solution, HCl gas is sent, whereas the sodium chloride solution, HCl gas, both are having chloride ions in common. Due to this particular common ion effect, this chloride ion concentration, increased concentration of chloride ion recombines with the sodium, thus sodium chloride precipitation occurs and it is taken out. Uses of the sodium chloride, and it is used as generally table salt in cooking and also used for the preparation of many compounds of sodium like sodium carbonate, sodium hydroxide, even preparation of sodium followed by the sodium peroxide. Such kind of substances are made with the help of sodium chloride as the source for the preparation of many of these varieties of sodium related compounds. Sodium. The important minerals related to sodium are rock salt, that is sodium chloride, chili saltpeter, that is sodium nitrate, cryolite Na3Al6, borax Na2B4O7 10H2O, sazimitti, that is sodium carbonate, and the mirabilite, sodium sulfate, and soda feldspar, sodium aluminium silicate NaAlSi3O8. These are the important ores, minerals related to the sodium. Whereas extraction of sodium is more electropositive. It never present in the free state. It is a metal, easily loses electrons. So by normal chemical methods in the laboratory, preparation of sodium becomes difficult. The only one method that we can left for the preparation of sodium is electrolysis method. The first method is Downs process, whereas in this process a steel tank is taken and steel tank is lined inside with the heat resistant bricks. It is having heat resistant bricks in the entire inside portion of the steel tank, and it is having T-shaped graphite anode as we are looking here, and the cylindrical iron connected with the graphite, surrounded with the graphite, is acting as cathode over here. So this is the cylindrical iron connected with the graphite ends or surrounded by the graphite ends is acting as connected with the negative terminal of the battery, and it is acting as cathode, and this is acting as anode. And in this, what happens is we are taking the mixture of sodium chloride as well as the calcium chloride. Pure sodium chloride and calcium chloride combination is taken. This mixture is here fusion mixture, whereas on heating, sodium chloride is having higher boiling point, whereas by using of calcium chloride, its melting point and boiling points decreases, hence it is easily converted to the liquid in physical state. Whereas in this apparatus, if you observe once again, here what happens is this particular T-shaped anode is covered with the a steel tank and having a dome at the top, because here the purpose of keeping the steel tank is whatever the oxidation takes place, due to that oxidation whatever the gas is going to be liberated, that gas is trapped in the location and it is allowed to escape from the system, not to react with the liberated sodium. For that a special arrangement was made. In the same way, at the both ends of the cathode, here a vertical tube is kept which is having some lower temperature, and here the purpose of this one is, here at cathode reduction takes place. Due to reduction, sodium undergoes reduction and sodium metal formation takes place. lithium undergoes reduction, calcium undergoes reduction, calcium metal also formation takes place. These formed metals are sent through this pipe into the container connected with that having of the kerosene, and here the solidifications becomes very easy for the calcium, hence calcium easily solidifies and falls in the fusion mixture itself, whereas sodium is having lesser density and sodium never liquefies easily, hence it will go through the pipe and it is collected in the kerosene. And whatever the chlorine is liberated, to not to make once again to interfere with the liberated sodium, these two compartments are separated one from the other. Thus in this way, in Downs process, by taking a mixture of sodium chloride and the calcium chloride as fusion mixture, we prepare sodium. Let us go for the chemical transformations and the reactions that are going to be taking place in the preparation of sodium by the Downs method. Yes, chemical reactions. At anode, oxidation takes place, at cathode reduction takes place. In oxidation process, the chloride ion undergoes oxidation and liberated as chlorine gas and escapes out from the dome followed by the outlet, and it is very valuable material. Whereas at cathode reduction takes place, calcium 2 plus is converted to calcium liquid in state, sodium plus 1 is converted to sodium liquid in state, but the solidification temperature of calcium is little, hence once again it falls in the fusion mixture itself, whereas liquid sodium, which is having lower density and the higher melting point, through this cooling pipe it reaches to the kerosene chamber and it is collected. Thus sodium is prepared. The second process in which the sodium is extracted or prepared is Kastner process, whereas this process is different from the Kastner-Kellner process. There is a big difference. Kastner process is different from the Kastner-Kellner process. Whereas in this the electrolyte is molten sodium hydroxide. This is the complete steel cylinder. Both anode and cathode are either made up of iron or the nickel. This is cathode and these two are the anodes. Whereas the temperature is less at the bottom, hence the sodium hydroxide is present in solid in state. Whereas at the top from here, this is neck, and from here temperature is high. Due to this high temperature, sodium hydroxide is present in fused state. Whereas the density of sodium is little compared to sodium hydroxide, hence it floats over the surface of the sodium hydroxide. And such kind of things are generally present. Let us go for the chemical transformations, how it is going to be extracted. Chemical reactions occurring in the Kastner process, whereas sodium hydroxide is present in the form of sodium plus and the OH minus. At cathode, that is here, the reduction takes place. It is separated from the anodes with the steel diaphragm, whereas that sodium plus after taking electron is converted to sodium, which is having lower density, hence it is collected over its surface like this. Sodium is going to be collected and it is separated from the sodium hydroxide as well as the anode compartment related components. Whereas at anode oxidation takes place, this OH minus is converted to oxygen followed by what? Here water molecules, and electron is liberated. Thus here oxygen gas concentration goes on increasing. Whatever water is formed, due to high temperature some of the water will be evaporated, and some water also once again present in the form of H plus and OH minus undergoes electrolysis once again. Here at cathode reduction takes place, H plus is converted to hydrogen. Thus here these of all are hydrogen molecules, pressure increases with respect to hydrogen, whereas OH minus the same, converted to oxygen followed by water molecules. Thus oxygen quantity is present over here, whereas hydrogen as well as the liquid sodium, otherwise because sodium is having lower temperature, lower melting point, the fused sodium is collected over the surface of the sodium hydroxide. Then after electrolysis it is collected. In this way, in Kastner process also we can prepare the sodium. The flowchart representation of the reactions related to the sodium. Whereas sodium is prepared by electrolysis process, one is Downs process. whereas the fused sodium chloride followed by calcium chloride and the potassium fluoride combination is taken. Second one is Castner process. In this, fused sodium hydroxide is taken. On doing electrolysis, sodium is prepared. Sodium on reaction with hydrogen forms sodium hydride. This sodium hydride on reaction with carbon dioxide forms sodium formate. Sodium on reaction with sulfur forms sodium sulfide. This sodium sulfide on reaction with sodium sulfide followed by iodine leads to the formation of sodium thiosulfate. Similarly, sodium on reaction with oxygen, sodium oxide. Sodium oxide with excess of oxygen leads to sodium peroxide. This sodium peroxide followed by carbon dioxide leads to the formation of sodium carbonate followed by oxygen. And in this process, instead of carbon dioxide, here oxygen is liberated. Hence, the starting material sodium peroxide is known as oxone. And this sodium peroxide on reaction with carbon monoxide, which is harmful gas, that is also taken by the sodium peroxide and it is converted to sodium carbonate. On reaction with sulfuric acid, dilute sulfuric acid, it is converted to sodium sulfate followed by hydrogen peroxide. Similarly, on reaction with benzyl chloride, that is converted to benzoyl peroxides. Similarly, on reaction with dry ammonia, sodamine formation takes place. This sodamine on reaction with water leads to the formation of sodium hydroxide followed by ammonia. On reaction with carbon, sodium cyanide followed by hydrogen. On reaction with carbon monoxide, extra oxygen is there, that oxygen comes and combined with the hydrogen, that is sodium cyanide followed by water formation. With respect to carbon disulfide, sodium thiocyanide followed by hydrogen sulfide formation takes place. Sulfur extra here, sulfur extra here. With respect to hydrogen, sodium hydride followed by ammonia formation takes place. With respect to N2O, reaction takes place and it is converted to sodium azide followed by water. This sodium azide on reaction with the sulfuric acid, it is converted to hydrozoic acid, that is N3H. The next important compound is sodium hydroxide. The sodium hydroxide is known as caustic soda because it breaks the proteins present in the body, that is protein present in skin, and it made that one into the pasty mass. Hence, it is said to be the caustic soda. Whereas preparations can be done by the following four methods. First method is causticization method, which is also known as Gauss's method. In this, sodium carbonate and calcium hydroxide are reacted. That is a reversible reaction. As a result of reaction, it is converted to sodium hydroxide followed by calcium carbonate. Calcium carbonate is less soluble, hence easily removable, and we can change the conditions to move the reaction to occur in the forward direction. Second one is electrolysis method by using aqueous sodium chloride. In this, aqueous sodium chloride is consisting H plus and the OH minus, whereas sodium chloride is consisting Na plus and the Cl minus. At anode, oxidation takes place, that is Cl minus is having lesser reduction, lesser preferential potential, that is it can easily undergo the oxidation process. So therefore Cl minus is converted to Cl2 followed by losing of electrons. Chlorine gas is liberated out at the corresponding electrode. Similarly, at anode oxidation takes place. Out of these two in competition, the preferential potential is present for the hydrogen and it is converted to H plus is converted to hydrogen gas followed by losing of electron. By gaining of electron, it is converted to hydrogen gas. That it is reduction takes place and here oxidation takes place. From here hydrogen gas is eliminated, from here Cl2 gas is eliminated. Remaining cation sodium plus and the OH minus combines and that leads to the formation of sodium hydroxide. And the next is porous diaphragm method. In this method is also known as Nelson cell method. In this, the electrolyte that we will use is aqueous sodium chloride. The next one is Kastner-Kellner method. In this, three compartments are there. Mercury is used as electrode, whereas the electrolytes that we will use in this case are aqueous brine sodium chloride solution and aqueous sodium hydroxide solutions are used. We will discuss this Nelson method as well as that is porous diaphragm method as well as the Kastner cell method in detail. Porous diaphragm method, which is also known as Nelson cell method. This Nelson cell method is consisting of perforated U2. This is perforated U type of steel tube which is having holes and which is coated inside with the asbestos and which is present in the iron tank. Outside it is iron made tank. Within this iron made tank, this particular steel tank is present. Whereas here the sodium chloride aqueous solution is taken as electrolyte, and here once again graphite rod is inserted into the cell which is acting as anode, and this particular perforated steel is acting as directly as an electrode, that is acting as cathode. Whereas aqueous solution of sodium chloride reaction liberates the hydrogen as well as the chlorine, so therefore separate outlets are made for the liberation of hydrogen and liberation of chlorine. Chlorine liberation takes place at anode, hence a separate outlet which conflicts with the hydrogen. Similarly, a separate outlet for the liberated gas hydrogen at the cathode is made an outlet. Whereas here reactions takes place in such a way that sodium chloride is present in the form of Na plus and the Cl minus, whereas at anode oxidation takes place. So therefore at anode oxidation takes place, chlorides are converted to chlorine, that chlorine is liberated from this particular compartment. Whereas at cathode what happens is, whatever the water is there, that water on reaction with the electrons given at the anode participates in reduction at the cathode. By taking those electrons, water is preferentially converted to OH minus followed by hydrogen. Through these perforated holes, whatever the hydrogen is liberated, that liberated hydrogen goes through the outlet. Whereas these OH minuses as well as the sodium plus, because it is cathode is having negative charge, this OH minus will come towards the negative charge. Similarly, the sodium plus will come towards the negative charge. That sodium plus combines with the OH minus. As a result, it is converted as sodium hydroxide. Through these perforated holes, the sodium hydroxide will comes out and it is deposited over the perforations. After certain amount of deposition of the sodium hydroxide through this valve, the steam is opened. As a result, it is hygroscopic in nature. It is converted to liquid in physical state. Otherwise, it becomes somewhat wet. That wet sodium hydroxide is deposited at the bottom. Thus, sodium hydroxide is prepared. The next method is Castner-Kellner method. In this, the cell is somewhat complicated. It is having partitions. 3 compartments are there. These two are set to the outer compartments and this is set to be the inner compartments. Whereas a mercury layer is kept at the bottom, and this mercury layer can be portable from one compartment to the other compartment, whereas a complete separation is not present. Whereas this outer compartment is having outlets for the generated gas, and at the same time here it is having graphite rods as anode, and here also the graphite rod is acting as anode. And in these outer compartments, mercury is acting as cathode, whereas in the inner compartment, that the same mercury is acting as anode, followed by a list of iron rods. A set of iron rods were kept from the top and these are acting as cathodes. Thus partition does not reaches to the bottom and mercury is brought into circulation. In the outer compartment the electrolyte is brine, and the middle compartment the electrolyte is aqueous sodium hydroxide, and the electrodes present in the outer compartment are anode as graphite and cathode as the mercury, whereas in the middle compartment anode as mercury and cathode as iron. Let us go for the reactions. What are those and how it is going to be taking place. Yes, reactions occurring in the Castner-Kellner process. In the outer compartment is same in Castner-Kellner process. 2 outer compartments are there. Here it is graphite rod is acting as anode and the mercury is acting as cathode, and it is filled with the brine solution. Brine is aqueous sodium chloride. It is consisting of H plus Na plus for competition, as cations and OH minus and Cl minus or anions are in competition. Whereas at anode, that is nothing but what graphite oxidation takes place. Cl minus is having the highest discharge potential, hence it undergoes the corresponding discharge. Cl minus is converted to chlorine followed by what? Liberation of electron. That chlorine is expected to liberate through a proper channel adjusted in the cell. Whereas at cathode what happens is Na plus and H plus are in competition, but due to formation of amalgamation, the though preferential potential, discharge potential is higher for the H plus, instead of H plus, because it forms an alloy, it forms an amalgam. So therefore in the formation of amalgam, that sodium plus, after taking electron, sodium and amalgam combination occurs and leads to the formation of sodium amalgam. Mercury can be movable from one compartment to other compartment in the eccentric wheel. If I adjust the wheel and the cast and Kellner cell will be moving ups and down, as a result this mercury and the mercury dissolved liquids are moving from one compartment to other compartment. So therefore the sodium amalgam is moving from middle compartment and outer compartment to middle compartment also. Whereas in the inner or the middle compartment we are having aqueous sodium hydroxide, that is water followed by sodium hydroxide, followed by now here sodium amalgam reached to the compartment. And here these are iron rods are acting as here cathodes and the mercury layer is acting as anode over here. So therefore at cathode reduction takes place. Whatever the H plus is there, that is water molecules takes the electrons and they are converted to OH minus ions followed by hydrogen gas. There is a proper channel for the liberation of hydrogen as a gas. Whereas here the sodium amalgam, whatever is reached to the middle compartment, undergoes oxidation process at the anode, nothing but at the mercury, and that leads to the formation of sodium plus followed by mercury by liberation of electron. This is nothing but what? Oxidation. Thus we are having overall sodium plus concentration followed by OH minus concentration. Thus the concentration, the strength of the sodium hydroxide present in the middle compartment is goes on increasing. Thus the sodium hydroxide preparation occurs by using of Castner-Kellner method. One smart logic to remember in case of the porous diaphragm method, that is Nelson cell method as well as the Castner cell method, is H plus ions are there as well as water molecules are there. Reduction takes place at the anode, that is H plus generally after taking electron is converted to hydrogen. But instead of writing this one, what we wrote there, water after taking electron it is converted to hydrogen followed by OH minus. The same thing happens here also. The H plus is produced from the equilibrium of water. If H plus is involved in the reduction process and it is converted to hydrogen, its concentration decreases. Automatically that leads to the increment in concentrations of what? OH minus. Thus, this is represented in such a way that water after taking electron, it is converted as hydrogen gas followed by what? Usually an increment of OH minus concentration. Everything appears to be different, but it is the one and the same. Sodium hydroxide is hygroscopic, that it will take the moisture from the water from the moisture. As a result, it is present in the form of 1H2O, 2H2O, 3H2O up to 7H2O. Whereas it is also having ability to be getting dissolved inside the water by taking excess amount of water from the moisture. Thus it is also said to be deliquescent. Thus by taking excess amount of water from the moisture itself only, it is getting dissolved and forms aqueous sodium hydroxide solution. Thus what we can say is it is not only hygroscopic, it is deliquescent in nature. Chemical properties of the sodium hydroxide. Sodium hydroxide is a base. It is a good alkaline base. It is present with the or associated with the OH minus ions, Arrhenius base. It readily combines with the counter property containing substances, that is nothing but acids as well as the non-metal oxides, that is acidic oxides. So therefore on reaction with acids like HCl, sodium chloride, sulfuric acid, sodium sulfate, nitric acid, sodium nitrate, acetic acid, sodium acetate, oxalic acid, sodium oxalate. These of all reactions are non-redox reactions. We can't find any kind of change in oxidation number of any of the system. Acid base reaction, neutralization reaction, salt followed by what? Water molecule formation occurs. Similarly, non-metal oxides like carbon dioxide, silicon dioxide, sulfur dioxide, it forms sodium carbonate, sodium silicate, sodium sulfite, formation takes place. Here also, we won't find any kind of change in oxidation number. Hence, these are also examples for the non-redox reactions. Reaction with amphoteric metals or amphoteric substances. Sodium hydroxide is base. Amphoteric is that one which readily combines with acid as well as the base. Here the base is sodium hydroxide. Zinc on reaction with sodium hydroxide, sodium zincate. Aluminium on reaction with sodium hydroxide, sodium meta-aluminate. Tin on reaction with sodium hydroxide, sodium stannate formation takes place. Here 0 state is converted to +2, oxidation. Aluminium is converted to +3, oxidation. Tin 0 is converted to tin +2, oxidation. And in this process, hydrogen is getting liberated, that is +1 is converted to 0, that is reduction. Hence the whole process is an example of what? Redox reaction. Reaction with non-metals. Sodium hydroxide on reaction with boron forms the boric acid. On reaction with carbon, a special reaction that leads to the formation of sodium followed by sodium carbonate and the hydrogen. And in every case, hydrogen gas is liberated. Sodium hydroxide on reaction with silicon, sodium silicate followed by hydration. The hydrogen, because it is oxidation, and here it is undergo reduction. Similarly, with respect to phosphorus, disproportionation reaction occurs that leads to the formation of sodium dihydrogen phosphide followed by phosphine. With sulfur, with less amount of sulfur, it gives sodium sulfide followed by sodium thiosulfate. With excess amount of sulfur, disodium pentasulfide followed by sodium thiosulfate. And on reaction with fluorine, it gives sodium fluoride followed by oxygen difluoride under cold and dilute conditions. Whereas if it is hot and concentrated, sodium fluoride followed by oxygen gas formation takes place. With respect to chlorine, it gives sodium chloride and the sodium hypochlorite under cold conditions. Whereas under hot conditions, it gives sodium chloride and the sodium chlorate, NaClO3 formation occurs. On reaction with ammonium salts, it is converted to ammonia followed by, this is HCl combination. Acid and base reaction occurs, thus water and the salt sodium chloride formation occurs. On behalf of the reaction of the sodium hydroxide with respect to the salts are divided into three categories. Some of them are forming insoluble hydroxides, whereas some of them are forming insoluble hydroxides, but they are soluble in excess amount of addition of sodium hydroxide. In the last case is they form hydroxide, but that hydroxide is unstable and it is converted to stable oxide. Thus, three varieties of reactions are there when sodium hydroxide is allowed to react with the salts. We will go step by step, one by one. The first one is which can form unstable hydroxides and which are not soluble. Case 1, salts which are reaction with sodium hydroxide forms precipitates which are insoluble and appears as precipitates with different colors. Nickel nitrate forms the nickel hydroxide. Similarly, ferrous sulfate forms ferrous hydroxide. Ferric chloride forms ferric hydroxide. Chromium chloride giving chromium hydroxide, and manganese sulfate gives manganese hydroxide. Similarly, the copper sulfate forms copper hydroxide. Everything is a precipitate. Some of the colors are like this. Here ferric hydroxide is red in color, chromium hydroxide is green in color, manganese hydroxide is buff in color, and similarly the copper hydroxide is having blue green in color. Yes, case 2, whereas these particular salts on reaction with sodium hydroxide forms corresponding precipitates, but on reaction with excess amount of sodium hydroxide, once again that leads to the formation of aqueous, that is soluble components. That is zinc sulfate forms zinc hydroxide, which is white color PPT, but excess of sodium hydroxide dissolves that zinc hydroxide in the form of sodium zincate. Aluminium forms aluminium hydroxide, white color PPT, but on reaction with excess amount of sodium hydroxide, it is converted to sodium meta-aluminate, NaAl. In the same way, tin forms tin hydroxide, which is white color PPT, and this on reaction with excess amount of sodium hydroxide leads to the formation of a new soluble complex, that is sodium stannate, Na2SnO2. As the last case, certain varieties of salts forms the hydroxides, but these are unstable and once again converted to stable oxides. Like silver nitrate is converted to silver hydroxide, which is unstable, and is converted to silver oxide, which is having brown color. And mercury chloride is converted to mercuric hydroxide, and once again that decomposes to stable oxide of mercury, that is mercuric oxide, having yellow in color. Similarly, reaction with carbon monoxide and reaction with sodium hydroxide, insertion reaction takes place, and that leads to the formation of sodium formate. Sodium formate formation occurs. Uses of sodium hydroxide. Sodium hydroxide is alkaline base, hence it is used as a reagent in the laboratory. In order to clean the glassware, the dilute sodium hydroxide is used, and also it is used in the preparation of soaps, petroleum industry, and in the rayon, paper and the pulp industries also the sodium hydroxide is used. In mercerization of cotton, this is most important useful application of the sodium hydroxide, and in the preparation of organic coloring materials like dyes. Near the electrical generators and the transformers, the sodium hydroxide is used because it is having ability to take up the liberated sulfur. And also it is used to prepare in the manufacturing of sodium metal. We will take the help of sodium hydroxide in certain cases, and also used to prepare many varieties of compounds of sodium like sodium hypochlorite, sodium chlorate, sodium cyanide, and some other important sodium related compounds preparation. We will take the help of the sodium hydroxide.